on doing incremental computation. So incremental computation is a set of methods so that you can produce a much faster calculation if you're only changing a little bit of a previously run computation. So your example could be like a spreadsheet where you change a single cell in the spreadsheet and watch some change in your chart, or a web page where you've changed just moved something over a little bit, but you don't want to relay out the entire page. Or a spell check. If you open up a document, the entire document is going to be spell checked, but then as you're typing, only a single word is going to be checked at a time. And I've been working with Adaption, which is a general purpose incremental computation engine, where the user just writes the regular from scratch algorithm, and it takes care of memoizing for you. And I'm happy to talk about this, but I need to move on. These are some of the advanced helps that it gives you. So really the problem here is that general purpose incremental computation requires a lot of memory, and we'd like to fix that. So the solution is just memorize fewer results. And that does work. You get less memory usage, less time to manage it, so you have better update times, and you get some control over this balance. But of course, there's some complications. Mainly, we can't use a strategy that's just memorize everything at every point. And we have to make the choice, and that choice is going to come with some difficulties. So I've been working with data structures. So we're going to add memo points to our data structures, and what these are is just memorize thunk that returns the next item in the data structure. So these are just components of the data structure that are memorized. So here's an example. We've got a list of arbitrary data, and we need to add memo points in here. So we're just going to add them evenly, and then we're going to do some computation, produce an output list. This is just, say, a mapping. And everything lines up really nice, and it works well. You modify some data, and only one memo point's changed. That's exactly what we want. Unfortunately, if you try to do an incremental insert now, it's not going to line up. More memo points are going to change than you need, and this fanning out does not scale at all. So what we need is some kind of probabilistic distribution, and we're going to do that by hashing each data point and putting a memo point in there if, say, in this case, the mod 4 is 0. Now everything's going to line up as well, but in order to get them to line up in this method, you have to create the new memo point in the output list when you observe the old one in the input list. And doing that, you can have an input, and things will just move over. And everything's in line, and that's what we want. But we've committed ourselves to referencing a previous memo point to create a new one. We can't just say arbitrarily create memo points in this new output, and that's not going to work. So this divide and conquer, we've used merge sort. We'll take this input list. Most places are memoized for the example. We're going to create a balanced tree out of it, and every time we reach a memo point in the input list, we place it wherever in the tree that we happen to be creating it. The problem here is that, the problem is, and then to do merge sort, we're going to have a recursive function over the structure and merge the branches all the way up the tree. The problem is that we reach these memo points, we reach the memo points before we reach the data. And so if we do this naive algorithm, we're just going to get all the memo points up at the top, at the beginning of the list, which is all the overhead, and we're going to get no incremental reuse from the rest of the list. So instead, what I figured out we could do is that we pass these memo points, we pass references to these memo points down through the recursive calls until you reach the data. And then we're going to maintain this association as we merge up through the list, through the tree. And now we get memo points as we want them, evenly distributed through the list. And this works pretty well. We have here a chart of running, inserting a single item and then demanding the entire list with various list lengths. And you can see that regular nominal adapton runs about 10 times faster than completely recomputing from scratch. And then sparse adapton is to do another about 10 times fold over that, 10 times improvement over that. And we're doing this to look for more and more complex algorithms. One I showed you is not too difficult to do, and probably everyone's tried merge sort at some point. And then as we solve these problems, we're going to put them into libraries so that the user doesn't really have to deal with this name distribution, and eventually try to work towards interactivity of common tools. So I mentioned spell check at the beginning. Maybe your IDE does spell check for you. Maybe it even does type checking for you as you type. We'd like to push that even further. Maybe program verification as you type. And that's about it. What I've said is we can increase efficiency by managing this overhead, but the placement of these memo points matters. And one solution that works is to associate them with data and maintain that association as you transform your data. So, thank you.
My impression when you write programs using this technique of incrementalization is that it helps to have a good mental picture of what happens in mind, because several equivalent programs may be less or more well suited to placing memorization points. With your sparse technique, do you need to rely less on understanding how it works? Does it work in more situations, or do you need a different intuition than what you had before?
So, like just about any optimization, handcrafting the code is probably going to work better until somebody comes up with a really great heuristic. But what we're trying to do here is build some libraries so that users who don't want to think about where to place these memo points can just use a library, simple lists, and tree structures, and it will do this automatically for you in some common general case.
Okay. Okay.
I actually have another question.
Sure.
I think it's related to that question. So, how exactly is what does sort of the code look like when you add all these elements?
So, like in this, well, even here. So in the structure of the tree, we just, instead of just having regular nil and branch and data, we just add another item that says memoize function, and it takes in a func or a adapton node in this case. That's in the data structure. And then for the library, there's just a case statement, select statement that once you get to one of these memo points, usually what the best thing to do when you get to the memo point is just to force the data and make a recursive call directly. And then there's a little bit more complication there. There's these references that I mentioned. These references actually have to be inside the structure as well, so they're called we call them first-class names. And when you reach one of those is when you usually create the next memo point, because that's when you have the reference. And so there's a few cases where you have to deal with each of the special items in the list. And that's why we're making the library, because a lot of these things there's a general formula for how they work.